we're going to evaluate a line integral for work now that's in differential form. We're given the line integral with the vector field written in differential form, and we're also given a curve, the square root graph from 0, 0 to 4, 2. So if I were to do a simple sketch, that would be from the origin, concave downward to the point 4, 2. So we need several pieces of information, but what we have here is, again, the vector field components, and then we need to turn the curve into an R of t parametricized form. So what is R of t? R of t, if you recall, we can use sort of function notation to write a simple function of R of t. If you let x equal to t, then it says right here that y is equal to the square root of whatever the x is, which would be square root of t. And then furthermore, since we know that the x goes from 0 to 4, we would then know that our time value, which is right here, is also from 0 to 4, because x and t are the same thing. So we have our boundaries for our integral, our limits of integration. We have R of t. What we need still is the velocity vector v of t. And the first derivative would be 1 comma, with power rule, 1 over 2 radical t. So now we have all the pieces. We have our x and y values, x and y right here. We have our velocity vector. We have our boundaries. We're all good to go. Let me just make some space. Make it clear here that we know that x is t and y is square root of t, and 0 is less than or equal to t is less than or equal to 4. And we have our velocity vector. So let's go into our line integral and let's set it up properly. Okay, here we go. So this line integral is equal to x plus y squared, comma 3x minus y, dot product velocity vector, which was 1 comma 1 over 2 root t. I have to slide up the screen to see that, with respect to t. We've proven this through previous work, that this differential form is equivalent to the dot product form we've just written. We also can now plug in what x and y are equal to, and the limits of integration from 0 to 4. So we'll set this line integral up. That will be equal to the line integral from 0 to 4. And where it says x, we put in t. Where it says y squared, we put in square root of t squared. Where it says 3x, we put in 3t minus y, which is the square root of t. Dot product 1 comma 1 over 2 root t with respect to t. I can do a little bit of cleanup, so maybe I'll do that before I get further into this. From 0 to 4, right here, that's t plus t is equal to 2t comma 3t minus root t, lost a minus sign, dot product 1 comma 1 over 2 root t. And if you get the sense that we're kind of an autopilot, we sort of are, as long as we understand our vector operations. We're now doing sort of the busy work of the calculating of this problem. So we're going to go 1 times 2t, which is just 2t. And we're going to go this times these two terms. So that's going to be 3t multiplied by 1 over 2 root t is going to be 3 halves root t. And then root t times 1 over 2 root t is going to be 1/2, all with respect to t. So each of these integrals these terms, excuse me, can be evaluated with just power rule. And let's see if I can do this without making any giant errors. So this antiderivative is going to be t squared plus 3/2 t to the 3/2 multiplied by 2/3 plus 1/2 t, and the boundaries 0 to 4 for this antiderivative. So we have 4 squared is 16. 3/2 times 2/3 is 1. 4 to the 3/2 power is going to be 8. And then I think I've lost myself a minus sign here. That's right here. That's minus sign, and that should be a minus sign. Shame on me. 1/2 of 4 is 2. And then if you let t equal 0, all of these terms are 0. And let's see what we have left. 16 and 8 is 24, minus 2 is 22. And that is the solution to finding the work of that vector field over the curved square root of x from 0, 0 to 4, 2. Easy peasy.